population P of bacteria in an experiment can be modelled by the formula P equals 100 e to the 0.4 t, where t is the time in hours after the experiment began. Use the model to estimate the population of bacteria 7 hours, so t is 7, after the experiment began. So if we substitute 7 into our formula, into our model, we've got 100 times e to the power of 0.4 times 7. And substituting that into your calculator, we get 1,644. And then I'm going to leave my answer like that to the nearest whole number for the population of bacteria. So that's my answer for part A. Part B, interpret the meaning of the constant 100. Well, this is the initial number of bacteria. This would be the value of the number of bacteria when t is 0. Because I'd have 100 times e to the power of 0.4 times 0. The 0.4 times 0 would be 0. E to the power of 0 is 1. So the population is equal to 100. So this is the initial population. Or you could say the population when t equals 0. Or you could say the starting population, anything along those lines. Part C, estimate how many whole hours after the experiment began does the population of bacteria first exceed 1 million according to the model. Right, so I'm going to take my model and I'm going to make that equal to 1 million to find out the time when the population equals 1 million. And then I can just go for the number of hours above that to work out when it exceeds 1 million. Right, divide both sides by 100. I'm now going to take logarithms of both sides to remove the exponential. It will be the natural logarithm of this side in this case, because the base is e. And then I can divide both sides by 0.4. So ln 10,000 divided by 0.4. On my calculator then. We get 23.0258, blah, blah, blah. So that's saying just after 23 hours, the population would equal 1 million. So how many whole hours will it be when it exceeds 1 million? Well, it's going to be above 23 whole hours, so 24 hours.